healthy vegetation and compare that to the spectral signature of unhealthy vegetation. Let's just remind ourselves how the spectral signature should be drawn. On the x-axis we have wavelength, which could be in nanometers from 400 to 2500, and on the y-axis we have reflectance in percent that goes between 0 and 100. And now let's think about the three main components of a leaf and how that affects the vegetation response. The leaf is made up of the palisade parenchyma, and the palisade parenchyma houses the pigments, the dominant pigment being chlorophyll. We know this pigment response drives our response in the visible part of the spectrum from 400 to 700 nanometers. In the near-infrared part of the spectrum, it's the structure of a leaf in the spongy mesophyll that's driving the effect. And then in the mid and shortwave infrared, it's the water in the leaf that causes the patterns that we see. Now let's draw a healthy leaf. We know a healthy leaf is full of chlorophyll. If it's full of chlorophyll, then it must be absorbing in the chlorophyll wavelengths, which is blue and red. So therefore we see dips in the spectrum in the blue and the red because the absorption is more. If absorption is higher, reflectance is lower. In the green part of the spectrum, there is no absorption because of chlorophyll, so we see a characteristic green peak associated with why we see vegetation with green. In the near-infrared part of the spectrum, we see a massive change. We see large amounts of photons bouncing around inside the leaf structure that ultimately go away and bounce back to the sensor. And as a result, we see very, very high levels of reflectance, up to 80% in the near-infrared part of the spectrum associated with the spongy mesophyll. In the mid-infrared part of the spectrum, water becomes the major impact. Leaves that are very healthy have lots of water. As a result, the photons are being absorbed. A wetter leaf will have more photon absorption. If there's more absorption, there must be less reflectance. So we see that high peak in the near-infrared part of the spectrum drop down as the water absorption starts to have an effect. We see a dip around 1500 that's associated with the water vapor in the atmosphere, and then reduction in reflectance down to about 20% in the mid-infrared and shortwave infrared part of the spectrum. Now let's contrast this healthy leaf spectrum with an unhealthy leaf. And let's preface this by saying that an unhealthy leaf is going to have less chlorophyll, breaking down in structure, and will be drier. With that in mind, let's think about the visible part of the spectrum. An unhealthy leaf has less chlorophyll. If it has less chlorophyll, it must have less absorption. If it has less absorption, it must have more reflectance. So therefore, we would expect the line in the red and the blue parts of the spectrum to be above that of the healthy line. The green may stay the same. So we still may be having a green leaf that's starting to lose some of its chlorophyll. So we expect the green reflectance to be similar, but the blue and the red to be higher. In the near-infrared part of the spectrum, there's much less bouncing around because the structure of a leaf is breaking down. The photons are not able to bounce around as much, and they start to get absorbed by the leaf itself. This absorption increases, causing a reduction in the reflectance. So we expect to see the line increase in the near-infrared, but nowhere near as steeply as it does for a healthy leaf. And ultimately, there'll be less near-infrared reflectance than for the healthy vegetation. In the driving of water in the shortwave and mid-infrared part of the spectrum, the leaf is becoming drier. That means there's less water. If there's less water, there's less absorption. If there's less absorption, there's more reflectance. So we would actually expect higher levels of reflectance in drier leaves in this mid-infrared part of the spectrum. So connecting those components together, we see that the vegetation spectrum of a dying leaf is in fact above the healthy leaf in the visible, below the healthy leaf in the near-infrared, and back above the healthy leaf in the near and mid-infrared, the mid and the shortwave infrared, as we move to that longer part of the spectrum.